Hello everybody! In this video we're going to continue our discussion of functional limits. So you'll recall in the previous video we gave meaning to an expression of this form. We called this the a limit of f. All right, and we said this was equal to L maybe if for every L coin we could find a punctured A coin such that the F image of that punctured A coin, at least intersected with the domain, lies inside this L coin. So our first job in this video is to give a sequential characterization of functional limits. All right, so let's write this down as a theorem. So this will be the sequential characterization of functional limits. Okay, so we're always very happy to take things back to functions where we have quite a bit of understanding already. All right, functional limits. Such a long title. Okay, so we're going to have some function f with domain D, and we're going to choose some point A, not necessarily in D, but at least should be a limit point of D. So the statement is going to be that the limit as x approaches A of f of x is equal to some real number L if and only if. So the idea is going to be that when we take the limit, we're just looking at punctured A coins, right? And trying to find ones that f is going to map into an L coin. But instead of looking at all possible points around A at once, right, to some punctured A coin, instead we're just going to look at D sequences that don't contain A, because remember we want a punctured A coin. So we're going to look at D sequences that don't contain A, which converge to A. And then we're going to see, well, what happens when you apply F to those sequences, and they should converge to L. Okay, so the statement is that the limit is L if and only if for every D sequence, but throw out A. So remember, these are sequences where the terms lie in D but are not equal to A. So for every D sequence A dot that converges to A, we have, when I apply F to that sequence A dot, this should converge to L. Okay, so that is the sequential characterization of functional limits. All right, well, let's do a proof of that. So, of course, this is if and only if, so it'll be two directions. So we'll start by assuming that the limit is equal to L. So the limit as x goes to A of f of x is equal to L. Okay, furthermore, since we're trying to prove for every D not equal to A sequence A dot that converges to A, something happens, then we're going to also assume we have such a sequence A dot. Okay, and that A dot is a D not equal to A sequence such that A dot converges to A. All right. Well, we want to prove that f of A dot converges to L. To show this kind of convergence, we need to put an L coin around L. So we do that by picking an epsilon. And we need to find a tail of the sequence f of A dot, which is contained in this L coin. Okay, well, what do we know? We know that the limit as x approaches A of f of x is equal to L, which tells me that the L coin of radius epsilon, okay, so let's write this. So since the limit as x goes to A of f of x equals L, the L coin, L minus epsilon, L plus epsilon, contains the F image of the intersection of D with some punctured A coin. Okay, so the L coin, L minus epsilon, L plus epsilon contains the F image of the intersection of D with a punctured A coin. Okay, let's call it A minus delta, A plus delta, not equal to A. Okay, there's the puncture. Okay, for some delta, which of course depends on epsilon, but we'll just shorten it as delta here, and some positive real number. Okay, but furthermore, we know that A dot converges to A, which tells me that for any A coin, and hey, look, I have an A coin of radius delta here, right? Maybe this is punctured, but just ignore that. If I have an A coin of radius delta, there exists a tail of A dot contained in that A coin. All right, so as A dot converges to A, we know that a tail is contained in this punctured A coin. Oh, wait, why did we say punctured A coin, right? Didn't we just say we know that there's going to be a tail which is contained in the A coin? But what do we know about this A dot? It's a D not equal to A sequence. So all of the terms in A dot are not equal to A. So they're not only in the A coin of radius delta, but they're even in a punctured A coin. So as A dot converges to A, the punctured, well, let's just write the punctured A coin, right? So we have A minus delta, A plus delta not equal to A contains a tail of A dot, right? It may not contain the entire sequence, but it contains a tail. Okay, so the claim now, though, is that if we know that this punctured A coin contains a tail of A dot, and we know that the L coin contains the F image of the intersection of this punctured A coin with D, and everything in A dot is in D, then we know that this L coin actually contains the F image of a tail. Thus, L minus epsilon, L plus epsilon contains a tail of, well, not A dot, but remember, this contains the F image of things in the intersection of D with this punctured A coin. So it contains a tail of F of A dot. Okay, and that's what it means, though, right, for F of A dot to converge to L. For every L coin, and this epsilon greater than 0 gives us our generic L coin, it has to contain a tail of F of A dot, and that's what we have. All right, so that's one direction. So now, conversely, okay, so in the converse direction, we assume that every D not equal to A sequence A that converges to A has the property that F of that sequence converges to L, and we want to prove that the limit, the A limit of F is equal to L. So we're actually going to prove the contrapositive statement, right? So we're going to prove not that bottom implies top, but not top implies not the bottom. Okay, so if the limit as x approaches A of f of x does not equal L, we want to find a D not equal to A sequence that converges to A, but whose F image does not converge to L. Okay, so that's the plan. So if this limit does not equal L, then there exists some epsilon, and let's call it epsilon star, right? So this is a specific epsilon. So there's some epsilon star, meaning I can find some L coin of radius epsilon star for which there is no punctured A coin whose F image is going to be inside the L coin of radius epsilon star. Okay, so let's write that out. There exists an epsilon star greater than 0 such that if I take the L coin of radius epsilon star, this contains does not contain, I should say, does not contain the F image of the intersection of D and any punctured A coin. Okay, so remember, if the limit is equal to L, then for every L coin, there would be some punctured A coin whose intersection with D has the property that when you apply F to it, it lies in the L coin. If the limit does not equal, then there must be at least one L coin for which there is no punctured A coin that will work. All right, so we have such an L coin now. Okay, fine. So let's take some natural number n, and I want to choose a point which I'm going to call a sub n. Okay, remember there's no sequence yet, right? And I want to build a sequence. I'm going to choose a point, and I'm going to call it a sub n in D, that lies in the punctured A coin of radius 1 over n, and whose F image is not in the L coin. All right, so let's write it and then we'll explain it again. So I'm going to choose a point an in D such that a sub n lies in the punctured A coin of radius 1 over n. Okay, so I toss out a, but I get everything between a minus 1 over n and a plus 1 over n. Okay, and, okay, well, there's a lot of points I could choose in here, but and such that if I take the F image, so F of an, this is not an element of the L coin of radius epsilon star. Okay, so the previous line guarantees that this can happen. If I take any punctured A coin, right, intersect it with D, fine. All right, so I'm only looking now at points that are in D and in this punctured A coin. I know that there must be some point whose F image is not contained in this L coin. So I choose one of those points. Okay, so this is not there's not one particular A, and for each little n, right, I'm going to choose some point an. And this is going to give me a sequence. Okay, so we define a dot equal to the sequence an, n starting at 1. Okay, now because I chose each an to be in D, I know that this is a D sequence. And because I chose each of these ANs so that they were in the punctured A coin, I know that this is even a D not equal to A sequence. Okay, that's first. Next, because I'm choosing these ANs to lie in these intervals, which are getting very close to A, right, namely this 1 over n, I actually know that this sequence of ANs has to be converging to A. Okay, if we want to make this precise, I can use the Archimedean principle. Right? So I claim that for any A coin, I can go out far enough, or I can get a tail of A dot, which will lie in that coin. So for example, okay, I've already used epsilon all over the place, so let me use the Greek letter gamma. This will be my radius for my A coin. Then by the Archimedean principle, by Archimedes, we know that there exists some positive integer m such that 1 over m is less than gamma. All right, but I also know that this 1 over n is a decreasing sequence. So since 1 over n is decreasing, if little n is at least big M, then, well, how far apart is A sub n from A, right? The proposed limit of my sequence. Well, I know that A sub n is in this A coin of radius 1 over n. So A sub n is within 1 over n of A. But because n is at least m, I know that 1 over n is less than or equal to 1 over m. But 1 over m is less than gamma. So I've just shown that as long as I go past m, right, so if I look at the tail, a greater than or equal to m, that this is contained in the a coin of radius gamma. Okay, so it follows that a dot converges to a. Okay, so I have found a d not equal to a sequence that converges to a. Okay, what happens to f? Because remember, my goal here, I was trying to prove the contrapositive form. My goal is to show that if the limit does not equal L, then there exists a d not equal to a sequence a dot that converges to little a. Okay, we found that. Such that the f image does not converge to L. Okay, but we know for all n, this was our definition, right? For all the n, for all n, f of an is not an element of the L coin of radius epsilon star. Which means that there is no tail of f of a dot contained in this L coin. Right? So no tail of f of a dot is contained in the L coin of radius epsilon star. And so this implies that f of a dot does not converge to L. Okay. So this finishes the proof. I'm going to write down one quick consequence, and then I think maybe we'll be done with this video, and we'll do some more properties in another video. So there is a very easy corollary of this. It's really just looking actually at what we did. So we're going to call this the divergence criterion. Divergence criterion for functional limits. Okay, so this is actually nothing new. It turns out it's just rewriting what we did up above. So I start with some function with domain D, and I have some limit point A. So we're going to assume that x dot and y dot are D not equal to A sequences, such that they converge to the same point. So x dot and y dot both converge actually to this limit point A. Okay, so we have two different sequences approaching A. So maybe you have A here, of course, that may not be in D, and I approach it one time maybe from the left. And then I approach it another time maybe from the right. Okay, so maybe this was my y sub n, right, or my y dot, and then over here this was my x dot. But they're both converging to A. Okay, and we're also going to assume that the limit of f of x dot is not the same thing as the limit of f of y dot. So even though x approaches A and y approaches A, when I apply f, I get different limits. So if this is the case, then the limit as x approaches A of f of x does not exist. Okay. And if we go back up to our sequential characterization of limits, then we can see this actually pretty easily. If the limit did exist, right, and it was equal to some L, then we would know for every D not equal to A sequence that converged to A, the F image of that sequence would converge to the same L. So if you know that you have two sequences, A and B, which converge to A, and their F image converge to different values, then this limit must not exist. All right, so that is our divergence criterion. And in the next video, we'll do some examples of this as well as writing down the algebraic functional limit theorem properties. All right, we'll see you next time.